Today we continue with our topic, integration. We now look at the second aspect of integration, which is definite integrals. We will extend it to look at some standard integrals. In definite integrals, we have the integration of the function f of s ds from the point A to the point B, which is equal to the integration of f of s ds evaluated at the point A and point B, which eventually will give you capital F of B minus capital F of A, where A is the lower limit and B is the upper limit. In the actual sense, in definite integrals, the constants of integration K is factored out by the information given to us. And the information is the use of the lower limit and the upper limit, which we substitute into the integral, and then of course the constant K factored out. So it does not involve, the definite integral does not involve the constants of integration K in the real sense of it, because it is factored out. Thus, the definite integral of a continuous function is equal to the difference of the values of indefinite integral at the upper and the lower limits. This is called the Newton-Leibniz formula. You know calculus, the father of calculus, they are the Leibniz and Newton. And so they also came up with this formula for definite integrals. We shall also look at some of the properties of definite integral. The first one, as expressed above, and I repeat here, is the integral of f of s ds from the point A, the lower limit, to the point B, the upper limit, is equal to the integral of f of s ds, after which you evaluate it at the point A and B, substituting B first because it's the upper limit, and we have fb minus fa. That is the first property. The second property is, if you are integrating a function from the point A to a point C, f of s ds, this will be equal to integrating it from A to B, f of s ds, and then from B to C, f of s ds. This is a situation where you have maybe a cubic curve which is both positive and negative or otherwise, and you are integrating it from one part to the other in such a way that there is at a point where it's crossing the x-axis and then it's also rising. So either falling and rising, or it's rising and falling. At these various points, we'll be able to find the values at those terminal points. And then, of course, we have this relationship. In order for us to eliminate K, where we are given the lower limit and upper limit, we will substitute the lower limit and the upper limit in the integral of the given function, as we have said earlier. Another situation we arrive where we are, that is in definite integrals, we could have the point x, y given, so that we will be able to find the value of the constant K. So there are two situations here. You are given the lower limit and the upper limit, you can then find the value of K, factor the value of K out. Another situation is that given the function, you can also be given the point S and Y on the S and Y coordinate axis, so that when you substitute the values of S and Y into that function, you also again eliminate the constant K. We shall take a look at an example on this issue. So the first example we're going to look at is example number 1. The gradient of a curve is 2x plus 7, and the curve passes through the point 2, 0. Here the gradient of a curve is given. We have to find the equation of the curve. Your solution, because you are given the gradient, what is gradient? Gradient is dy all over dx. and this gradient is equal to 2s plus 7. And that the curve that we get, the function, the curve passes through the point 2, 0. But before we get there, what then is the function? This is the gradient of the function. What is the function? To get the function, we now have that you differentiate the, integrate the y and equal to 2s, the integral of 2s plus 7, also with respect to s. So in other words, this and this will cancel, leaving you with y equal to, you now integrate this becomes 2s squared all over 2 plus 7s, and then plus the constant of integration. Good. And of course, this will cancel this again, so leaving us with s squared plus 7s plus k. Then at the point 2, 0, what do you now have? 0 will be equal to, your s is 2, so that is 2 squared plus 7 times 2 and then plus k. When you now solve this is 4 plus 14, that is 18. So our k therefore is equal to minus 18. Therefore, your y is equal to your s squared plus 7s minus 18. And this is the equation or the function for where you have the gradient as 2s plus 7. Here is the second example. Evaluate s squared minus 1 ds from the point s equal to 1 up to the point s equal to 3. That is from the limit 1 up to 3. Our solution, once again we have the limit and the function to be integrated with respect to s. Of course, this will give us, integrating this one, you have s cubed all over 3. If you integrate this one, you have your s. Then you evaluate this at the point where s is 1 and the point where s is 3. The upper one will be substituted first. That's 3 raised by 3 all over 3 minus 3. Thereafter, you subtract, open the bracket. You are now substituting the lower one, 1 raised by 3 all over 3 minus 1. You close the bracket. This gives you 27 all over 3 minus 3. And then this gives you minus 1 all over 3 and then minus 1. The result will be 9 minus 3 minus 1 over 3 plus 1. And so this is equal to 6 plus 1 is 7. And 7 minus 1 over 3 is 6, 2 all over 3. And this is the solution to the problem. Example number 3, evaluate the integral 2 cos 4s ds from pi all over 12 to pi all over 4. Solution, we first of all integrate the function given to us. So we write 2 into cos 4s ds. If you integrate this, you have 2 multiplying 1 over 4. If you differentiate cos, what do you differentiate to get cos? You differentiate sine. So this will be sine 4s. So if I differentiate sine 4s, I will get cos 4s. So if I now integrate this, I will now have 2 times 1 over 4 sine 4s, which will be equal to half of sine 4s. Now we are going to evaluate that from the point pi all over 12 to the point pi all over 4. So this will be equal to, substituting that value, let's say we're now evaluating it at pi over 12 and then at pi over 4. Pi over 4 is the upper limit, so we now have this to be equal to half times sine 4 and our s is now pi all over 4. Everything here minus your half, and you have sine 4. Our s is now pi all over 12. So then we simplify this to give us half sine 4. We cancel 4. That will remain as pi minus half into what we have here now is sine of pi all over 3. First and foremost, we must recall that we have half in this place. So this means we have the sine of pi all over 2 minus the sine of pi all over 6, 2 times 3. Now we recall that our pi is equal to 180 degrees. So we have sine of 180 all over 2 in degrees. And then we have this as sine 180 also all over 6. This will give us the sine of 90 degrees, and this will give us the sine of 30 degrees. They are both special angles. Sine 90 is 1 and sine 30 is half. So the final result is equal to half. That is the correct answer. Let us look at some standard integrals. The first one is the integral of a times s to the power n ds will be equal to a s to the power n plus 1 all over n plus 1 plus the constant of integration. We have been using this formula. The second one is sine as ds. You can see it becomes minus 1 over a cos as plus k. You will recall that if you differentiate minus cos as, you will have plus sine as. That is why the solution is like this. This becomes the function f of s. The third one is cos as dx. If you integrate this function, just like the second one, you will have 1 over a sine as plus k, because if you differentiate sine as, you will get cos as. Followed by this, we are familiar with the first three. Now here is others. To integrate sec squared as dx, you will recall that from differentiation, if you differentiate tan s, you will get sec squared s. So now, if you are integrating sec squared as, it means that you need to differentiate tan as to have sec squared as multiplied by 1 over a plus the constant of integration. Then the next one, cosec squared as dx will be equal to minus 1 over a cos as plus k. Because if you differentiate minus cos as, you will get cosec squared as. The sixth one, cos as, cot as. These are standard integrals, just like we have standard differentials. So here, this will be equal to minus a cosec as plus k. You just need to study the variation in each of these ones to recognize how to write out the integrals. The seventh one is sec as tan as dx. This will be equal to 1 over a sec as plus k. Because if you differentiate 1 over a sec as, you will get this function. The eighth one, exponential e raised to power as dx. If you now integrate this, you will have 1 over a e raised to power as plus k. And the ninth one is 1 all over as dx will eventually give you 1 all over a log as plus k, because 1 all over s, the integral of 1 all over s is logarithm of s. So the integral of 1 all over as will also be the log of as. Multiply that by 1 over a plus k. The 1 over a is this value when you differentiate it. And then you now take that variable and then of course the inverse of it to multiply the integral. These are some of the standard integrals. You need to know them offhand so that sometimes in examinations they are very, very handy in solving some problems.